Okay, now we're going to talk about thermal expansion. Now this one's a good one because we went over our mechanical properties recently and we learned about something called strain, okay? So we learned about something called strain. That was change in length over my initial length, or sometimes change in length over initial length. It's written several different ways, but it's just a fraction. It says how much based on your initial length did you actually stretch. Now, what you probably realize is that most materials, not actually all of them, but most materials actually expand when you heat them up. Some materials don't. There are a few, usually human-made materials, that actually contract based on craziness in their lattice structures when they heat up. So what we realize is that if we can actually look at how much our material strains, this right here, this has the exact same units as strained. It's a change in length over our initial length. It's going to be equivalent to the change in temperature multiplied by some special coefficient, which is the linear coefficient of thermal expansion, which is usually in per degree Kelvin or per degree Celsius. In this case, it doesn't actually matter. You don't have to convert because when it comes to temperature change, they're the same. Temperature change does not require a conversion. But same can be said if it gives it to you in Fahrenheit, and then you're going to have to, and you have this in Celsius, well, then you're going to have to convert. But usually you can look these things up. Also, not all materials have a linear coefficient of thermal expansion. Some are going to be second order or third order. They might have some strange equation for it. But for this class, we're going to only deal with ones that are linear. Now, where does this come from? Well, we talked about this a little bit earlier about how as we go from one step to the next, our bond gets further and further up. And these bonds are stretching as we increase the energy, and the energy in this case is equivalent to our temperature. So we increase the temperature, that causes the bonds to vibrate back and forth more, which changes their interatomic distance. So they're no longer stable down here, they're actually stable up here now because we increased the temperature. And so because the bonds are stretching, we have thermal expansion. So this microscopic property from individual bonds going to stretched out bonds is leading to our macroscopic expansion. Okay. Now, most cases it's asymmetric, though there are a few cases where we can pretend that it's symmetric and that this just is a parabola. And that's a nice little way to solve for it, at least right here towards the bottom. Most of them can be approximated as this. Now, the big thing it's getting at right here, though, is that our change in bond length is actually coming from the asymmetry. I mean, if you're trying to calculate energy levels, you do this actually in quantum physics. This is great, but our change in bond length is coming from the lack of symmetry. Because in this case, even though they're bouncing back and forth, this is their nice radius right here. That is where they come to a nice stable point. In this case, though, as they continue to move further and further away, where they are stabilized, their radius is actually much, much higher. It gets further and further up. And so this would not lead to expansion, but this would. Okay. Asymmetric leads to expansion, symmetric does not, and that's not super important for us. We're just going to assume that everything expands. But if you take a quantum physics class, when they start approximating things like this, so you can calculate energy levels, just remember that's approximations. Okay, so let's look at thermal expansion comparison. What you can see right here is that, well, wait a minute. What's going on here? Okay, so polymers, once again, have very high coefficients of thermal expansion. They had high heat capacities. Now they have high coefficients of thermal expansion. Metals, kind of the middle, and ceramics, pretty dang low. Now let's think about why this might be. Why do you think the polymers have such high coefficients of expansion? Well, once again, it's because of all those twisted up members, which are, guess what, very, very good at stretching. Because what's going to be loosening up first is not the bonds themselves, not the covalent bonds between individual atoms in the polymer, but those van der Waals bonds, those secondary bonds that are holding the individual polymers together. Those weaken very quickly, and because they do, these expand very quickly. Metals, nice lined up, non-directional bonds, just sitting in a sea of electrons, and so they're also very, very happy to expand. Ceramics, ionic bonds are also technically non-directional. However, they have an issue in that they have a positive charge next to a negative charge next to a positive charge. And all that's good and fine and dandy, but if I try to expand, I'm actually trying to force a positive charge closer to another positive charge. And it doesn't like that. I'm moving it away from a negative charge it wants to. And I know there's a negative charge in between here, but there's another positive charge over here. And so they're going to start moving towards each other, and they're going to resist that. These bonds are much stronger than metallic bonds, okay? And so they want to stretch less. You can actually look at the coefficient of thermal expansion. It's a good marker of the strength of the bond, how deep that well is. So our coefficient of thermal expansion typically decreases with increasing bond energy. The stronger the bond, the less it wants to expand. Okay, bye-bye. That's it for this one. So thank you for listening, and I'll see you all next time. Bye-bye.